This video is to show you some of the changes that are being made to the modeling instruction curriculum for chemistry to focus on proportional reasoning throughout the materials. In this video, we will describe the rationale for the changes and show you several tools for students to use with examples from 4 different units. These ideas are also discussed in a teacher reading, The Story of Quantitative Reasoning. They will point out to you at the end of the video. One fundamental goal in science is to find how one aspect of nature may affect another. In doing so, we hope to uncover relationships we can use to explain phenomena and make predictions. In chemistry, there are numerous proportional relationships at the core of understanding matter. There are 2 ahas that kind of led to this approach. These provide a framework for helping students understand quantitative reasoning they need in chemistry. One is to distinguish between measured quantities and relationships and the relationships that exist between them. These have different roles in how we interpret what we see. So quantities such as mass or volume, or relationships such as density or molar mass. The second aha has the power of a simple definition. 2 quantities are proportional if they change together by the same multiplier or its reciprocal. If one doubles, so does the other. We want to give students quantitative foundations to build on. A core idea behind modeling instruction is the use of representations. This is as critical for mathematical reasoning as it is for science concepts. We will show you various representations of proportionality, as well as multiple mathematical strategies you can use. We want students to have conceptually grounded tools to choose from. There are numerous opportunities for students to use proportional reasoning in chemistry. By using a consistent set of strategies and representational tools in each of these areas, we give students the opportunity to learn more easily to transfer their knowledge to a new setting. And as we know, that is a critical skill in learning. Density is an area where we have proportional reasoning and do not have to rely on graphs and equations for understanding. For example, a student may be given a simple density, such as 6 grams per milliliter, and be asked to diagrammatically solve a problem. The bingo chip diagram lets students physically group 1 gram chips into 1 milliliter groups to find the mass of 5 milliliters. Student will discover that means we need 5 times the 6 grams, or 30 grams. Another approach is the block diagram, where one block is representing 1 milliliter that each has a 6 gram mass. Following the idea that the 2 are proportional and they must change together, when we double the volume, we automatically double the mass to 12. Then again, when the volume is raised to 5 milliliters, we now see that we have to multiply that original relationship by 5. Likewise, there are multiple mathematical strategies that are useful. In the first, 2 ratios are set equal to each other. One ratio is the known ratio of 6 grams per milliliter. The second ratio needs the mass. Students typically follow the algorithm, with varied success, of cross-multiply and divide. A conceptually more straightforward approach is to realize the new volume is 5 times larger than that shown in the density, so the mass must also be 5 times larger. Another approach we're calling a proportion ladder begins with the 1 milliliter equal to 6 grams. But how can a mass be equal to a volume, you may well ask? Well, it is better to say they are equivalent because they both describe the same piece of matter, and hence the use of the equal sign. Once again, we see 1 milliliter is 5 times larger than 5 that 5 milliliters is 5 times larger than 1 milliliter, then 6 grams must also be 5 times larger. The more traditional approach multiplies the known volume of 5 milliliters by the density. But rather than canceling units, we note that 5 milliliters is 5 times larger than 1 milliliter. It could be shown by writing the 5 milliliter in ratio with the 1 milliliter on the second part there, which is the multiplier needed to finish the reasoning. Each strategy prompts students to find the proportional multiplier that is given in the known parts of the data.
Consider this example from Unit 2, where we examined the PVTN behavior of gases. You may already use the table shown at upper right, but the graph provides a cue that volume is directly proportional to the number of particles. Since the number of particles decreases, the volume must decrease by the same ratio. In example 2, two variables affect the volume. The table, graph, and diagrammatic representations help to determine what multipliers to use. Since T increases, the ratio TF over TI must be greater than 1. Since N decreases, the ratio NF over NI must be smaller than 1. Note, the multipliers end up unitless because they compare like quantities. Proportional reasoning works with multi-unit ratios like heat capacity. The following slides show how C relates energy, mass, and delta T. Consider this thought experiment. Energy is added to both samples of water, but since sample 2 has twice the mass, it's reasonable that the same temperature change would require twice as much energy. Q is proportional to M. In scenario 2, the mass of water is the same, but the change in temperature is 3 times as great. From the graph in the icy hot lab, students should conclude that 3 times as much energy must be added to cause a tripling in temperature. This is shown in the proportion ladder. If both mass and delta T are changed, 2 multipliers must be used. Q2 must be 6 times as great as Q1. So Q is proportional to the product of mass and delta T. We can replace the constant proportionality with an equal sign and a constant. Consider a familiar example from math. The circumference of a circle is proportional to its diameter. Double the diameter, double the circumference. But to get a value, you need the proportionality constant. In this case, it's pi. C is equal to pi times the diameter. Here, the proportionality constant is the heat capacity, C. We've shown how the equation is derived. But is it needed to solve problems? Just like other ratios like density, we read from the bottom up. 4.18 joules per gram degree Celsius means that for each gram of water to raise its temperature by 1 degree Celsius, about 4 joules of energy must be added. Consider the problem below. Students can estimate the final answer by using proportional reasoning and then work with more precise values.
One way that could be approached is with a proportion ladder, where we see the heat capacity written as an equivalence of 4.18 joules being equivalent to 1 gram multiplied by 1 degree Celsius. When we could look at the values we have, we once again see that the mass increases by 50-fold and the temperature by 20-fold. So the energy must also go up times 50 times 20 or by 1,000. More traditionally, we can see it written out according to the equation, but we still need to recognize that we are still comparing 50 grams to 1 gram and 20 degrees Celsius to 1 degree Celsius to get the two proportional multipliers in order to get the answer. Chemical reactions are another common application of proportional reasoning. The secret is in Unit 7 to lay the foundation by illustrating the proportionality of a reaction in diagrams where every instance of the simplest ratio is grouped together both before and after the reaction. Each loop represents each reactant or product coefficients in the balance equation. Illustrating the reaction both before and after the reaction sets the stage further for BCA analysis in Unit 8. In this example, students are given the amount of each reactant before the reaction, as well as the amount of one reactant that will be used up. Notice that in a BCA table, the equation line and the change line both represent the reaction, so they must have a common multiplier between them. The silver nitrate data provides us with the multiplier of 0.05. 2 moles of silver nitrate must be multiplied by 0.05 to get 0.10 moles. Now we simply apply the same multiplier to every other coefficient to maintain the proportional relationship within the reaction. The BCA table is just a giant proportion ladder. The more traditional approach upon inspection reveals the multiplier of 0.05 for silver nitrate. This keeps reinforcing the idea that proportionality means all related quantities change by the same multiplier.
So the story of quantitative reasoning can be found as a reading in the chemistry resources available on the AMTA website. You can use this link to see a non-narrated version of the slides. We'd like you to encourage you to consider hosting a modeling instruction workshop. To do so, contact engage@modelinginstruction.org or check out our website.